So this is the scenario, and this is our required first question. This part asks for the step by step plan a design parking system. We need to draw a diagram showing how to counter, sensor, and display work together. So this is my answer. The block diagram shows how all parking control system connected work together. It starts with a keypad to the set maximum parking capacity. Here for four cars, the entry and exit sensor feed data into 3-bit up-down counter, which keep track how many cars are in the garage. A computer checks if current car count matches maximum capacity. If garage is full, timer one, 7-segment display shows full. If space available, display blinking. Then this is the flow diagram. Also includes all essential components like the encoder to process the input, register, and the clock synchronize operation. Each block a specified role ensuring the system of accurately monitoring parking space, update the display of real time. This visual layout understands the flow of data control signal between the different parts of the system. For the counter design, for the counter diagram design, uh, for this question, uh, I used 3-bit up-down counter up to up to seven up to 4 cars, which required 3 ZK flip-flops. Flip-flops is JK flip-flops toggle based on the previous clock and previous state, enabling the synchronizing counter. For question two, uh, for question two, uh, here here we can see that for question two, focus on 555 timer duty cycle and 7-segment display to recognize it's about circuit design for the parking display. This question required to design two separate circuit using 555 timer control to different display behavior. The first circuit continuously display word full, and second circuit display space available when there is parking space. This timer needed to blink the message based on the calculated duty cycle and frequency. For for counting duty cycle, I used formula d equal to 100 minus p, where p count I where p count where p count using my ID. Then so duty cycle becomes 80% and frequency 5 hertz. The capacitor for the capacitor uh, 50 microfarad. This is the high time and this is the low time. And for this and 250 for 250 microfarad. This is our high time, and this is our register and to registers values, and also this is our for this is for 70 microfarad. This is the two registers values. So the 47 microfarad for the row register drawing 2 ohms current, and 50 microfarad show the very high register. Here we can see that. Now move on for FSM and HDL code. Question 3. This question requires a state machine design the control, the display output A and B, and its Verilog code, ensuring the following given time limits. The FSM has to clearly define the state A, where input A active for the duration T is equal to 4 and a millisecond, and state B output B active for the TL equal to 4 millisecond. Also, I created a state diagram. A state diagram to visually represent to a state transition, and a state table defines the current state. Next state output A and B. Output A and B counter values required to the state transition. So to implement the FSM, I wrote the with state register. I wrote the Verilog code with state register and counter. The next state determined based whether the counter has reached value TH and TL. Switching between a state A and B, the output is simply assigned A when the state A and B, I state A in the state B. The counter reset in every state transition, ensuring processing time is for output period. Now question 4. Question 4. Finally, we analyze the system's weakness and the suggest improvement, like adding microcontroller for the larger parking areas. So this is my identified limitations. Here, no power backup, sensor bounce and false triggering, limited capacity. Here we used 3 bit. If I